In this work, we introduce RAR, a new solution for image restoration based on an efficient restore, assess, and repeat process. So, how does RAR work? The general idea is that given a degraded image, we rely on an image quality assessment model that can describe the dominant degradation in the image using free-form text. We then use the identified degradation as conditioning to a generative all-in-one restoration model. We then iterate between the two modules until we reach a stopping criterion or we're happy with the restored image basically. However, to maximize synergy between these two steps and ensure efficiency, we introduce several modules to make the entire process operate in latent space. First, we align the latent space of the IQA and the unified image restoration model. Basically, instead of using the original IQA encoder, we replace it with the restoration model encoder and introduce an image adapter AI to bridge their feature spaces. Training proceeds in two stages. First, we align the adapter output to the IQA encoder representation using a simple MSE loss. Then we perform end-to-end fine-tuning following the original IQA losses. We then use the output of the IQA to condition the restoration module. Our restoration module is based on Stable Diffusion 3.5, which takes text input as conditioning. We can directly take the text describing the degradation as written by the IQA. However, this implies expensive and lossy text decoding and encoding. So to avoid this, we introduce a conditioning alignment step. Specifically, we project the IQA output into the UIR conditioning space through an adapter AQ. As depicted in the bottom right of this slide, this adapter is trained to match the embeddings produced by the restoration model's text conditioning branch. So the alignment is optimized here again in two stages. First, fine-tuning AQ using a simple MSE loss again, and then jointly training it with the UIR model. These two alignment modules enable our RAR process to be more efficient and end-to-end trainable. The entire model is finally trained using flow matching. However, here again we introduce an important modification to the flow matching formulation. Specifically, in standard flow matching formulation, the model is trained to learn a mapping from noise to target distribution while using the degraded image as extra input. Instead, we propose a noise-free flow matching where we directly learn mapping from the degraded image distribution to the target distribution. This definition offers several practical advantages in the context of iterative restoration. For example, the model avoids the accumulation of noise-induced errors across multiple refinement steps. More importantly, the clean latent trajectory enables our LQA module to reliably assess the intermediate latents without being affected by added noise. With all these modules in place, the last requirement of our RAR process is to decide on when to stop the iterative process. To devise a stopping criterion for the proposed RAR process, we again use the LQA model. Our LQA model is based on Depict QA. This is an IQA that can compare pairs of images. We therefore re-enlist it to define a stopping criterion. Specifically, after every T steps through our model, we use the LQA to compare the quality of the images before and after restoration, or before and after a specific step. As illustrated here, in this case, the LQA takes previous and new latents as input, and it is tasked to compare the quality and yield a binary decision to either continue if the quality of the new latent is better than the previous, or stop otherwise. We evaluated our model on all standard publicly available restoration benchmarks, and as we can see here, we outperform previous state-of-the-art across various metrics and datasets. Importantly, comparing wall clock time, we can see that we achieved these results while being significantly faster than competing methods. In addition to qualitative results, as shown here, our RAR model can correctly identify the dominant degradation in each step and consistently yields higher quality images than previous state-of-the-art, either all-in-one or agentic models. If you want to hear more or learn more, come and check our poster and feel free to play around with our publicly available code.